let's go on to 8c. The ideas in 8c were, first of all, we wanted to think about how to compute far future values of cash flows expected in the future. And let me see if I have a cash flow diagram for this. I do. Okay, so this is good. So I'll leave it to you to review the wording here, and I'll just jump into this cash flow diagram. So what we mean by this is our far future values of cash flows received in the future is we're sitting here at t equals 0. We're going to get some cash flows at some time in the future, and each one of those cash flows is going to be growing by its interest rate r. And we want sometime in the far future, which is t equal 3 here, to know what the total future value of all these cash flows is. So in this case, we're sitting here at t equals 0. We're going to get a cash flow in a year, we don't have it yet, of 25. We're going to get a cash flow in 2 years of 25, and we're going to get a cash flow in 3 years of 25. And the question is, how much money is going to be in our account a nanosecond after we get this cash flow of 25? Well, it's pretty straightforward. This one we get in a year, it has 2 years to grow. So we're just going to use the future value formula. The future value is equal to the present value times 1 plus the interest rate. We've said in this example, the interest rate is 9%, raised to the amount of time it has to grow, which is 2 years here. 3 minus 1 is 2, or you can just count from here, 1, 2. So how big is this one going to get? This one that we get at end of year 2 has 1 year to grow. So it'll be 25 times 1 plus r raised to the 1, and that grows to 27.25. The one we put in a nanosecond before we pull our money out of the account has no time to grow, so that's just going to be 25. Then we just total up everything that's in the account. 25 plus 27.25 plus our 29.7 for the 25 that's had 2 years to grow. We add them all up, we get 81.95. So that's what we're thinking about when we're talking about far future values of cash flows expected in the future. Very, very straightforward. Then the heart of 8c was really all about compounding periods. And everything up to 8c was done in annual compounding with r% interest per year, and t was a real number with the units, importantly, in years. So we had our consistent units, r compounding per year and t measured in years. And we want to be able to do monthly compounding, quarterly, daily, etc. And all we have to do to make that work is just consistently change our time units for r and t, right? To make sure we consistently change those. So a couple of important things. So if we're establishing a quarterly compounding period, for example, we say r% interest compounded quarterly. That means this interest is paid every quarter, and we call this our native interest rate for quarterly compounding. And then in using this quarterly example, we're going to say that t equal 1 would mean 1 quarter from now, but in general, t equal 1 is going to mean 1 compounding period from now. So if we were working with monthly compounding, t equal 1 would mean a month from now. With semi-annual compounding, it would mean 6 months from now. And t equals 0 always means end of period 0. So here are some examples for native interest rates. So r equal 5% compounded annually. That's what we've done to date. R equal 6% compounded monthly. R equal 2% compounded quarterly. That type of thing. And then we developed this notion of the equivalent annual interest rate, or said in some texts as just the equivalent annual rate. And we developed this because oftentimes in the real world, you're going to look at a project with, say, 5% compounded annually and want to compare it to a project with 6% compounded monthly. And how do you do that? There's no good way to do that without getting our compounding units and time units consistent across projects. And the EAIR is what allows us to do that. So let's look at its formal definition. So the EAIR is going to be the interest generated per dollar we have in a project, irrespective of compounding period. So that's an awesome thing, because now we can compare projects with R compounded monthly, projects with R compounded semi-annually. We'll just get the EAIR for all of them, and then we've got them in this apples to apples annualized basis. So what's our formula for EAIR? You need to know this. Start with your native R, right? Start with native R. Okay, and then you just say the EAIR is 1 plus our native R raised to the number of compounding periods per year minus 1. And then we had to sadly bring the nominal APR into the mix because it's used to advertise many consumer loans, and also it's used in many bond examples. So what is our nominal APR? It stands for nominal annual percentage rate, and it's defined to be our native R times the number of compounding periods per year. So again, this R here is our native R, our native interest rate. And we're going to say, sometimes you'll see just APR, sometimes you'll see nominal APR. For us in this class, if you ever see APR, we assume it means nominal APR. So here are some usage examples. If we have a native R of 7% compounded annually, our APR would be 7% times 1, or 7%, and we would describe it as our nominal APR equals 7% with annual compounding. If we have a native R of 10% compounded quarterly, then our APR would be 10% times 4, or 40%. And how would we describe it? We would describe it as our nominal APR equals 40% with quarterly compounding. Okay, and knowing that, we can always get back to our native R by just dividing our APR by the number of compounding periods that are described in its definition. Okay, so APR is common but not usually helpful. So what we want to do whenever we see an APR is we want to convert it right away, convert to an R. We never want to put an APR in any of our time value equations. So convert it to a native R. What do? We just divide it by the number of compounding periods per year. That gives us our native R. And then we can compute an EAIR from that R, right, using our EAIR formula. Here are some good rules that'll always lead you to the right answer for problems where you have an APR to worry about or an EAIR to worry about. So thing number one is we always want to convert APRs to native Rs before using any of our time value equations, because the APR, as we know, is really a useless quantity, so it doesn't work in any of our time value equations. So why do we torture ourselves with APRs if I'm telling you they're useless? Again, because they are used, usually for nefarious reasons, by many banks, etc., in their advertising. They also come up in some of our bond examples. Okay, so second thing is whenever possible, once we get rid of that APR, once we've squashed it like a bug, we want to solve our problems in our native units for R and the corresponding time units. So for example, we get our R into 6% compounded quarterly, and then we're going to measure T in quarters, not in years or days or months or something like that. And then third rule is use EAIR only when you need it to solve a problem. So I might give you an EAIR and ask you to find the R. I might give you an APR and ask you to find the EAIR. So in that case, you'll have to go from APR to R to EAIR, that sort of thing. So if you follow these three rules, you should always get the right answer for problems involving APR and EAIR. And if you're interested in knowing why, I know that at least one of you out of 450 are interested in why, hopefully more. You can read all about it down here, and I explain why these rules need to be applied to ensure you always get the right answer. Okay, and then we looked at an important application for both EAIR and APR, and that was bonds. And most corporate and treasury bonds are not amortizing, which we'll talk about a little bit later, but they do pay their interest twice a year, so that's important. And we looked at bonds issued in real-world bond markets under two circumstances: at issuance, and these are things you've just got to memorize. You've just got to know these definitions. So the principal of a bond is the amount borrowed per bond. The face value is the principal to be repaid at the end of the contract per bond. And for us, that's why it's going to be the same thing as the principal, and also heads up, that's called in some places par value. So for us, principal equal face value equal par value. And the coupon is the total amount of interest paid per year per bond. And we've got to remember that 50% of this is paid every 6 months. So we can get from the coupon a coupon rate, which is the coupon divided by the face value. That's going to be written as a percent. Once we've got all that in our pocket, at issuance, we can get the APR for the bond, which is always just going to be the coupon rate. So we describe that coupon rate exactly as we describe any other APR. So it would be X% interest compounded semi-annually. And then we can always get our native R for these bonds by just taking our APR, dividing it by 2, because we have 2 periods per year. And then we can find the EAIR once we have the native R, and that'll help us compare various bonds. And finally here, I know there's a lot of terminology here. In bond land, at issuance, the equivalent annual interest rate is called the yield to maturity. After issuance was the second time that we considered bonds like this, real-world marketplace bonds where interest is paid semi-annually. So after issuance, the purchase price of the bond is going to be determined in the marketplace. Okay, so it's not necessarily going to be equal to principal or face value. So we're going to have to, as a result of that, we're going to have to find our native R based on the current bond price and the contract stipulations. We can't find R from the APR anymore in general, and we're probably going to have to draw a cash flow diagram to find that R. Once we find the R, we can find the EAIR, and this is still same as YTM. We looked at a couple of examples, but I think this is worth repeating here just to really hammer home how we have to think of things after issuance with bonds. So let's look at this one. On 112X1, Simple Company issued a bond maturing on 1120X7. Okay, so that'll be 6 years later with a $1,000 face value and a 10% coupon rate. Okay, so today it's 12X6. Okay, so they've just made a coupon payment and the bond is trading at 950. Let's find the native R and the YTM, and remember the YTM is just equal to the EAIR. So what do you want to do with this? There's really nothing for it but to draw this cash flow diagram. Okay, we just need to think about what are all the cash flows if we buy the bond today. So if we buy the bond today, we're going to pay $950, okay, and we're going to get this bond has a 10% coupon rate, so that means it's going to pay $100 every year. But remember, the coupon is paid, 50% of it is paid twice a year. So that's how I got the 50 here. Okay, so 50 equals 100 divided by 2. And how did I get that? 100 is equal to 10% of 1,000. So that's how I got my 50. So we know that half of the coupon is going to be paid in 6 months, and the other half is going to be paid in 12 months. And that's the end of the contract. So that's when we're also going to get the contractual face value back. So here's our cash flow diagram, and now we would treat this just like any other 3 cash flow problem. And what we're missing here, what we need to solve for here, is R. We know the cash flows, we know when they occur, we've just got to get R. Okay, so I've got here the equation for R that I use to solve for R, and I found that R is equal to 7.769%, which you could get from trial and error just plugging into this equation. Just keep trying some R's until the right-hand side of this equation equals 950. Then you have the right R. If you're using Excel, which you can't during an exam, you could do a similar thing, but tell Excel to find it for you. Or you can use, as we looked at previously, the quadratic equation. And again, I don't expect that I'll give you a lot of problems where you're going to have to use the quadratic equation, but I think a good thing for me to ask would be, what would be an equation to use as a start point for finding R? And then this would be the answer to that question. And the way you'd get that would be by looking at this cash flow diagram. Okay, so once we have the R, we know the YTM is equal to the EAIR, we know the formula for EAIR, and we just plug that in. And so the yield to maturity would be 16.2%. And with the yield to maturity in our pocket, we could compare this potential bond to many other potential bonds.